Okay. Hi, everybody. Today lecture is has the same content as the previous one, which has number 20. In this lecture, we are going again to optimize the sixhump function by using LabVIEW. We shall plot the function in three-dimensional space, and we shall plot also the contour plot for this function. Then we shall optimize the function and find the possible local and global optimal values. And at the end, we shall use a specific LabVIEW function where we can find only the global minimum and animate the motion of the particles in a two-dimensional space. The figure in front of you represents the block diagram which is used to plot the sixhump function. In order to do that, we use plot surface VI and plot contour or three-dimensional contour plot VI, and we shall use also the evaluation of f of x1 and x2 VI. These three functions or VIs exist in LabVIEW library. If we go to the front panel here and right-click on it, we go to the graph and three-dimensional graph here. Here you see a surface graph, VI, and also a contour, three-dimensional contour graph, VI. If you right-click, for example, the surface graph here and plot it somewhere on the front panel, as you see, and if you go to the block diagram, you will find a terminal for it, which is shown here. This terminal exactly is what we are using here. Plot surface in 3 dimensions. This is not necessary. Now we cancel it. We also can do the same. Go to the front panel and to the graphs and also 3-dimensional graph. And we can also use the 3D contour graph here. As you see, this is at the front panel. If you go to the block diagram, its terminal is this one, which is exactly the same as this one. So now we know how to plot or how to use the plot surface VI and 3D contour VI also. Each of them has 3 input terminals. If you look at the plot surface here, you find this terminal, X vector. This is the other one, Y vector. And this 2-dimensional is a matrix, Z matrix. This includes the information related to the XY values, XY arrays. Each of them is two-dimensional, and practically they demonstrate the value of Z in a mesh grid function. The three inputs to the plot surface are taken from the outputs of the evaluation y equal f of x1, x2. This function is existing in a mathematics palette. If we go to the script and formula, 1 dimension and 2 dimension, you find it here. If you write what it is called, it is evaluate y equal f of x1, x2 vi. If you want to see what it is and some basic information about it, so you go to the help, and here you see the inputs are an array which represents the start coordinates, another array which represents the end coordinates, start and end, here they are. And here you see an input and another input, where we can write the formula which you are going to optimize and the variables included in this formula. So this string here, the upper one, where we write the formula, and the other string where we write the variables, which are two variables indeed. Now at the output, as you see, we have here three outputs, one-dimensional array, again, which represents the input, and the other input, x2, and the output of the mesh grid here, which is y or z, two-dimensional. These three outputs now will be connected to the 3D graphs. So if you go backward, now this is not necessary for us, we connect this output to the input here, and the same also to the input x vector, and the other input y or x2 is connected here, and the same is connected also here. And the third one, which represents the mesh grid, here it is not seen, I can show you. Yeah, so this is the third output connected here and also connected here. The string here represents the variables x1 and x2. I call them x and y because in the representation or the equation of the function, we use x and y. And this terminal or string represents exactly the formula which we are going to use. If I right-click it here, here is the formula, as you see, which represents the sixhump function. Don't worry about these equations or functions. These are Rosenbrock and Holder table functions which we used before. They are kept in case we need them. We just go to the terminal of the Rosenbrock and connect it, or the Holder plate and connect it, and of course we can change the variables if they are not x and y, if they are x1 and x2, or they are also x and y. Here x and y, here x and y, and here x and y. So they are the same. Important for the start array, we define the bounds of the function the lower bounds and the upper bounds. The lower bounds between -3 and -2, and the upper bounds between 3 and 2. So the first variable varies between -3 and 3, and the other variable between -2 and 2. These values are given here in these arrays. If I double click here, I go and see the lower band, and if I double click the other array, I see the upper band. Now, if I run the program at this arrow, I get this figure, which represents the sixhump function, and at the same time also the contour function, which is represented in the XY plane. Of course, you can have a look at the contour function in 3D presentations. Here you can see the contours around the figure in 3 dimensions. Also, you can, of course, rotate this function the way you want, the angle you need. You can also manage the number of levels which are used in the contour here. As you see, we have here one contour, one level, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you right-click here and go to 3D plot properties and go to the contour to edit it, so we can see that the levels here, the number of levels is 10, as I did. We can minimize them, adjust them as we want. Suppose we want them to be 5 levels. Okay. Now, if we go here, we can and count them. We have 1 level, 2 levels, 3, 4, and 5. So it depends on what you want. You can also adjust it really by not only adjusting the levels, but here I go to the contour, but also by adjusting the intervals. And here you have the intervals. Suppose I want the interval instead of 8.9, I want it to be 18.9. I click it here and go back. Now I have another, as you see, plot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it continues to more and more values. It depends what do you want. So as you see, to plot the sixhump function is exactly in the same way as we did with the Rosenbrock or with the Holder table functions. The only thing you need is to take care of what are the symbols of the variables and what are the bounds of the function, and then you will get exactly the same answer. So I think we do not need to expend more time. And of course, if you want to look at the contour function in the, for example, the XZ plane, you can have a look. And here are the contours, or the ZY, also you can have a look. Or in the 3D, you have the possibility also to have a look there. So we finish with this program, and we move to another program where we optimize the function. We need to find the minimal values. As I told you in lecture number 20, this function has 6 local minimums. 2 of them are global. So the total are 6, and the two global minimums have exactly the same value. So there are practically five, one of five, and the sixth one is a repetition of the global minimum. In LabVIEW, really we have a better ability by using find all minima in dimensional VI. Here n is two-dimensional we use. So we use this function. As you know, this function exists in the mathematics and optimization via find all minima in the, this is the virtual instruments which we are working with. Of course, you can yourself refer to the help to know more about it, but really it is a very powerful and very interesting VI. In Python, we were able only to extract or to find the global minimum. But in LabVIEW, really, as you see, I have, okay, let me go to the block diagram and show you some details about it, then we will be back to the front panel. So in order to optimize the sixhump function, we introduce the function itself, f of x, which is, as you see, the same as we did when we created the plot, and also the variables, the string as a string, this is also a string, and we also introduce the start and end points of the bounds. The start and end bounds will be the same, minus 3 minus 2, 3 and 2. As you see, it's really very simple. Everything is done so that you can use it directly. You do not need here to import any arrays or do any things as we did in detail in Python. Here also, you have to decide what is the function you are going to use here, conjugate gradient with or without derivatives, as you see here. And if you cancel this one, let me cancel it. Sorry. And I cancel the other one. Okay. Edit. Remove broken wires. And now again, I right-click here, gradient method, or here, this method, which is called line minimum. So I right-click on the gradient method, create a constant, and I have here a window where I can select from it the method I want. Here it is selected Fleischer-Reeves or Pollack-Rebree. It depends what do you prefer. Also here, the result will not depend on this. They will be practically the same. Here also, sorry, I move it, yes, like this. Without derivatives, I shall use it without derivatives. You have also to select with or without derivatives. Okay, so as you see, you just configure the methods or functions which are going to be implemented and the bounds of the function, of the objective function, the expression of the objective function as a string, and the variables which represent the variables of the objective function. Here there is a terminal to show you the accuracy practically, which is associated with this function, exponent of order -8 is very high accuracy. You can manage it also. You can create, you can add here or adjust it to -6 or -5 if necessary. This is good because sometimes you find it difficult to catch every minimum value, so you can lower the requirement here, so that you can catch up more than the higher number of local minimums. At the output here, we find an array here with the positions or locations of the minimums, X values, and here we find also another array which represents the fitness, which represents the value of the objective function for each of these locations. So if we go now to the front panel and consider what we have, of course there is an indication here. I have turned it to show you that there is no error at all with the program and the program is correct. So the variables which we have, x1 and x2, start and end bound values here, and here is the function, and this is the result. What do we have? Here is the coordinates of the local minimum values which we have. They are 5, as you see. One of them should be the local minimum, the coordinates of the local minimum, and here is the fitness or the value of the function at each of these positions. This is the one position, x and y, and these are the values of the function. Remember, the value of the function is 1 minus 1.3, if you remember, or you can refer to lecture number 20. So it is here found twice, really. And if you go to this is the first one, if you go to the first one, you find it has an x minus 0.12 and the other one 0.72. Practically, this should be exactly the same as this one, which is where it is here, the last one. Null, as you see here, it is 0.7, here minus 0.71, 0.07. Remember, this really the value which we have got when we tried to find the minimum, the global minimum with Python. Because I told you that they have the same value as a minimum, but the coordinates are different, and I told you then that the sign of the x and y will change. Here it was about minus, let me say, 0.1, 0.7, here is plus 0.7, now here it is minus 0.71 plus 0.7. This value really is closer to the value which we have got with using Python. The other values represent local values. Let me demonstrate with you how it works. If you run the program now, you may not catch all, you may not follow up or find all the minimum values at once. You may have to repeat the cycle. If I run it now, I have got, as you see, 4 local values. One of them is the local, no, 2 of them here, as you see. The first one, 3 of them are shown here the same. But as you see, really the first one is very close to the real, and the second one is very close, but the third one here is far away. This is a local minimum, and this represent the global minimum. If we run again, here we have only one value of the global minimum, which is number 2.72. Here it is 0.08. In Python, I remember it was minus 0.08. It was, and this was 0.71. So as you see, they are very near to each other, of course, and gives you reasonable values. And the most interesting that at the same time you can find most or all the minimums. If I run once again, here we have 4, there are 3. Now, as you see here, we have 5 values. How many of them are global? 2 of them are global, the first one and the last one. This one is closer to the real one which we have got before. Okay, I think with this now it is clear how to work with the program. Don't save. And now I want to show you how we can find only the global minimum by using also another specific function for LabVIEW. As I see, really, LabVIEW work is very nice, and everything is done for the user to directly use the program and find the optimum values. And if you compare it with the Python, in Python you need to always construct the program in detail. The function which we are going to use is global optimization VI. Global optimization VI. If you go to the mathematics and from there to optimization, you will find it here, global optimization function, global optimization VI. This VI finds the global value only. It doesn't care with the local minimums. So it gives you the minimum value only. I have explained to you how this function works by calling dynamically the function which you are going to optimize, which usually you write and keep it in a file. And when this program, which is the main program, is run, it calls the program which is already established alone here. This is our function really of here x1 and here y, x and y, or x1 and x2, and this is the output, which is the objective function. Now, as you see, if we run the program, that function will be called in and will be optimized. In order to optimize it, of course, here you need to show the bounds of it, -3 or -2, and -2, 3 and 2. These are the variable, the bounds of the function. The function itself, as you see, is written here, given here. You do not need to do anything with it. And all you need maybe to manage the number of the iterations and the number of the particles which are going to be used. At the output here, you find the answer as an array which represents the coordinates of the output minimum. And this is the fitness or the value of the objective function minimum value here. And if you use this ending state cluster and open it here, yes, here you can, let me show you, sorry. You can unbundle it and see the internal elements, and you can use them to have an idea about the population, for example, which is the number of the real number of particles which exist. And here the I represents the number of the iterations which are running. So if we go backwards now to the front panel, here we have a display which will show the particles and how they converge to the minimum value, the global minimum value only. And also you will find the number of iterations, and you will find the coordinates x and y where the minimum value occurs. And you will find the value of the function or the fitness of the objective function. Here you see it was seen only as minus 1.316, and this is x, very close to the value of Python, and Python 0.85, here 0.89, exactly the same, and here minus 0.71. But the sign here may change because we have two values, two globals. If I run it, now you will see the particles, how they are converging to a point here. You see the number of iterations going on, and these are gathering and gathering closer and closer to the value. And you see also here the new coordinate and new value. If you consider these values here, the coordinates, here x and here y is about, here y about plus dot, this is 0, this is 1, this is 0.5, 0.6, 0.7. So this is at the level of 0.7 here. And x is equal, as you see, here minus 1, here 1, here is 0, it's about 0. As you see here, it is minus 0.9 or 0.1. Here it is, if this is 0, it is in the minus side. Practically, it is the same. So really, it works fine. Let us run it, stop it, and run it again to be sure that it gives exactly the same answer. Yes, this is minus, this is plus, exactly the same answer. Let me again run it. Now, if you notice, the signs have changed. This becomes minus 7, and this becomes plus, and now they are back. It depends. So, but they are the same, and the value here, it is the same. Okay, so with this, now we have found the minimum or the optimized number of objective functions to find their local minimums and to find their global minimum by using different functions, by using Python and by using LabVIEW. What is left here? One interesting thing I want to talk with you about in the next lecture. How we can use in detail the PSO or particle swarm optimization algorithm, because all the exercises which I illustrated to you were carried out by using the Python swarms, which is really a very nice library and has a lot of facilities, especially for visualization. But you may ask yourself how it works internally, and can we use it directly without the work done by the engineers who have modified the basic algorithm to be handy and easily used by the engineers when using PySwarms. So this will be the subject of the next lecture. It will take some time to illustrate it to you, and I shall also run it with one or two examples for you to be sure and to feel confidence with the basic particle swarm optimization principle. Okay, with this, we finish today the lecture. I wish you the best. Thank you very much. See you in the next lecture.